So it's my pleasure to introduce Ryan Johnson from Twisthink. He's their lead vision system engineer, and he's passionate about solving resource-constrained vision problems. And he's going to share some experience around optimizing performance. Ryan?
Thanks, everybody. Wow. You guys made it to the end. This is the last presentation. I think you guys all get like gold stars. Or are there any cookies left back there? Maybe we can bring those and pass them around. Everyone can get a cookie. Early in my career, I was given a really exciting challenge. My boss sat me down and explained how the next product was going to include a camera-based detection system. And I remember the dingy conference room we sat in, no windows, 90s style furniture and everything. And he described his vision for the product, requirements, and then he said, hey, you know what? The performance of the algorithm needs to hit 99%. Do you think we can do that? And I had no idea how to answer that question. I felt a little hair stand up my back of my neck, and I got all flush. So on one hand, I believe we could do it. On the other hand, the path to getting there and the requirements, to hit those requirements and the performance requirements to hit that was just really unknown. But not wanting to pass up a good challenge, I said, sure, we can do that, and we went for it. And the next year was full of twists and turns and ups and downs, but in the end, we were successful, and the product is in the market today still. Through that experience and many more like it, I've collected a series of best practices around vision-based detection systems, and I'm going to share one of those with you today. Start your algorithm development with the imaging subsystem. I'm going to give you 2 reasons why you should, and then I'm going to give you 3 practical techniques that will help you do that effectively. At Twisthink, we engage in these types of challenging problems every day, and we've been doing that for about 2 decades. We partner with companies to bring new products and services to life using intuitive strategy, intuitive design, and intuitive technology. We're a group of technologists, industrial designers, and business strategists, and our passion, really why we exist, is to help companies create new business value. And we do that for Fortune 100s down to entrepreneurial startups across a wide variety of markets, which gives us that kind of cross-market pollination that we're hearing about in the keynote this morning. We're located near Grand Rapids, Michigan, which is on the other west coast, is what we say, which is kind of like saying the other white meat maybe, but not exactly. We create products and services using these capabilities that we have on the bottom here. Embedded vision, AI and algorithms, connectivity, embedded system design, Internet of Things, and on the ends we have UX and UI, and then also human-centered design. And those are our bookends because we believe that great products are human-centered and they're desirable and usable. Today's discussion is going to be focused on vision-based detection systems, which broadly includes your object of interest that's in a scene, the environment that you are imaging that object of interest through, the imaging subsystem, which includes a light source, a lens, and an image sensor in this case, and then the digitized or captured scene with the object of interest, and finally an algorithm that is operating on that scene and extracting that and detecting that object of interest. I'm going to spend most of my time focusing on the imaging subsystem, and just a quick note, that the techniques I'm talking about here apply broadly from traditional computer vision approaches all the way to deep learning and our machine learning approaches. So why should we start with the algorithm development? Start the algorithm development with the imaging subsystem. The first reason is that algorithm performance is limited by image quality. This is the garbage in, garbage out concept. You can continue to throw more capability at your algorithm, but at some point, the performance is going to be limited by your image quality that you give it. Image quality is determined by the parameters, ultimately, of that imaging subsystem. The second reason is that imaging subsystems are complex. There are a lot of parameters that go into making that image quality, and those are split across multiple physical components. Often, it's very expensive to change those further down in the development cycle. So for these reasons, start your algorithm development with the imaging subsystem. And I'm excited to talk to you about 3 practical techniques that you can use to increase your effectiveness at doing this and be successful at it. They are iteration, sampling and sharpness, and evaluation. And when you start with your algorithm development with the imaging subsystem, just remember iteration, sampling and sharpness, and evaluation. I'm going to start with iteration. At the beginning of development, it's often hard to know where to start. There's a lot of ambiguity. There's a lot of uncertainty. And on one hand, with the detection system, the algorithm is going to drive your imaging subsystem parameter requirements. On the other hand, the imaging subsystem, the image quality produced by it, are going to drive the algorithm requirements. The good news is that Twisthink is creating a detection system crystal ball, so we're going to be able to solve that very easy. But in the meantime, what we have to use is iteration to help us through this. And we've adopted a framework called the Build, Measure, Learn loop, which is based off of lean startup practices to increase the effectiveness of that iteration. So what it does, what the Build, Measure, Learn loop does, is it gives you focused learning that's built upon previous learning. And so this is kind of how it works. When you start an iteration, the first thing you ask yourself is, what do I need to learn? And that learning needs to be based off of previous learnings. Then you ask yourself, in order to learn this, what do I need to measure? And then third, you ask yourself, in order to measure that, what do I need to build? And then you only build what's required for that learning. Now, if you take a step back from iteration, what you're really doing is finding the right solution. You're finding a solution that's optimized for your business goals, to meet your business goals. And that solution needs to be viable from a business standpoint, it needs to be technically feasible, and it also needs to be desirable, something that people will want. Now, we believe that a right solution from a vision detection system standpoint is going to harmonize the capabilities of the algorithm with the capabilities of the imaging subsystem. And that might look like different things for different applications. In one case, you might put more capability into the imaging subsystem. In the other situation, you might put more capabilities into the algorithm. Either way, it's the developer's responsibility to navigate and make those trade-offs as they iterate. So let me give you a quick example of what this might look like. A while ago, we were asked to design a camera-based linear barcode reader. Imagine a very dynamic scene or dynamic environment where the barcode reader can move in any direction at different speeds. There's barcodes all over the environment. They're at different angles, different distances from the barcode reader. They might have different sizes, different print quality. What we wanted to do was collect as many barcodes with a single image snap across a wide field of view using low-cost hardware and decode as many barcodes as possible with one single image snap. And the way that this iteration worked, the first iteration was just understanding what kind of, what type of camera we were going to need to solve this effectively. So that was our learning focus. In order to learn that, we believed we needed to measure the image quality that it would produce and the ability for the detection algorithm to decode with that image quality. And then, in order to measure that, we needed to build a camera, collect a small data set, and a first rev algorithm. At the beginning, we decided we need about 2 pixels of resolution across the smallest module width. And so that led to a 6mm focal length lens, a 5-megapixel rolling shutter sensor. Through this iteration, what we learned was, of course, the baseline cost for that sensor and camera. We learned that if we added more capability to the algorithm, we could reduce the sampling of the image sensor and save cost. We also learned that motion blur was by far the biggest noise source that was affecting our decoding quality. So we took those and we fed them into iteration 2, which focused on solving that motion blur issue. And we devised a way using a global shutter sensor and short exposure time. And in order to learn that, again, we wanted to measure image quality and the ability for an algorithm to decode barcodes with that image quality. And then we needed to build, again, a camera, collect a data set, and refine our algorithm and use that. So in this case, we used off-the-shelf dev kits to build the camera. We targeted a global shutter sensor in this case and changed the field of view with the 5mm focal length lens. We refactored our algorithm to use lower resolution images, and we focused on high motion scenarios. And from that, we learned, hey, the global shutter solution worked well. So that was motion was no longer a major source of error, and that we could even further reduce sampling, saving costs in the hardware by adding more capability to the algorithm. So this kind of continued. We did a couple more iterations, focused learning based upon previous learning. And we ended up on a solution that was right for the business. And, sorry about that. So, again, the big thing here is that we use build, measure, learn loops for focused learnings. That gave us more effective iterations, and we were able to land on a solution that met the business goals, one that was viable, desirable, and usable. So I've given you an approach. I've given you an approach to navigate when you start with the imaging subsystem, navigate the ambiguity. Next, I'm going to talk about sampling and sharpness. These are 2 high-impact image quality factors that when you start with the imaging subsystem, we believe you should focus on these first. Sampling and sharpness are two key components of a higher level image quality factor known as spatial resolution, which defines the smallest detectable object and feature that you can detect in an object. The sharper your image is, the more sampling you have, the smaller the object is that you're going to be able to detect in the image. When we develop a detection system, typically we split spatial resolution into sampling and sharpness because they're pretty complex. There's a lot of parameters in the imaging subsystem that drive those, and it's just simpler to look at them independently. So let's look at sampling first. Sampling is really pixel count over a given area. Usually the units are pixels per inch or pixels per millimeter. Sampling will vary with object distance, and that's a function of your optical system's magnification. So when you define a sampling requirement, it's usually good to specify it at some distance, say 20 pixels per millimeter at 6 meters away. Insufficient sampling reduces discriminating detail. Here's an example. It's a little bit difficult to make out what that is. It could be a coin. It could be the top of a Coke can, maybe a hubcap. As we add sampling, it becomes clear that that is indeed the top of a Coke can. So what do you need to know, and how do you determine your sampling requirements? There's three things that you need. You need to know the size of your smallest distinguishing feature. You need to know your maximum detection distance. And then you need to have a pixel count across that feature that the algorithm is going to use for identification. At the beginning of the development, it's usually a good rule of thumb to start with about 4 to 5 pixels across that distinguishing feature. This gives you enough margin to deal with some difficult situations. Now, in some cases, especially with deep learning and machine learning, you may not know what your distinguishing feature is. In this case, it's just best to oversample, and you can always decrease sampling digitally. And then once you have an algorithm in place, you can do a sensitivity study to understand how that resolution affects the performance of the algorithm, or how the algorithm performs with different resolutions. Driving those sampling requirements into the imaging subsystem parameters is actually pretty easy thanks to thin lens equations. And this is especially true for optical systems that have little to no distortion. And what you're doing when you drive into imaging subsystem parameters, you're affecting the image sensor pixel count, the image sensor pixel size, and the lens focal length. So the really cool thing about using thin lens equations is you can do a lot of analysis on paper before ever purchasing components and getting them in hand. So you can get kind of a good direction on your camera right from the beginning. And the way that we do that effectively and efficiently is we've created an Excel worksheet that allows you to put in image sensor parameters and understand how they affect sampling. And we have it available on our website, so feel free to download it and check it out. If you have questions or if it's not working right for you, just give me a call and we can work through that. If your optical system has more than 5% distortion, then those thin lens equations fall apart because now your resolution across your field of view is no longer linear. In that case, you're just going to need to buy components and try them out in the lab and measure it yourself. Sharpness is a measure of spatial frequency. The units are usually cycles per millimeter or line pairs per millimeter. It's kind of complex, and I have links to it on the resource slide, links to more resources around this if you're interested. In an image, sharp edges have high spatial frequency content. Blurry edges don't. And often discriminating detail has a high frequency content in it. So when you add blur, you're reducing discriminating detail. The best way to understand sharpening requirements is really to do a sensitivity study like we were talking about earlier. And I have a deep learning example here. We took a training set, trained up our algorithm. We kept some of that data for the test set. We tested the performance of the algorithm using the test set, and then we modeled blur, in this case using a two-dimensional Gaussian blur function. We changed the blur with different levels of standard deviation. In some cases, the two-dimensional Gaussian blur function may not be the right simulation for blur for your application, so you may need to choose something else. But basically what we did is we took the test set, augmented it with those different levels of blur, and tested the sensitivity of the algorithm to that blur. And you can see, as we added more blur, the performance fell off. So to drive those into requirements, what you need to do is decide how much performance you're willing to sacrifice for this component of the image, and then you can take that Gaussian blur function at that standard deviation, compute the magnitude of the Fourier transform, and that will give you sharpness at different frequencies that you can use for your requirements. Driving those into the imaging subsystem parameters is often complex because there's just so many parameters that go into this and are affected by it. So the way that we deal with that is we split it into two scenarios. The static case, which includes just no blur, no motion, and then the dynamic case, which is all about motion. In the static case, there's three primary influencers. There is the environment, the lens, and the image sensor. In the environment, anything that's between your imaging subsystem, your lens, and the object you're trying to image, that can affect your sharpness. So things like dust and fog and rain, any kind of lens surface contaminant, and usually those are uncontrollable, and you need to leave some margin in your system to deal with those or to accommodate those uncontrollables. On the lens side, of course, the lens quality and the quality of the focus relative to the image sensor is going to drive the sharpness of your image. Don't forget about temperature. An optical system is a mechanical system in the end, which will expand and contract with temperature. And also, lens-to-lens manufacturing variation will be a component from a sharpness standpoint. On the image sensor side, it really comes down to pixel crosstalk, which is a function of the wavelength of light. On the dynamic side, motion speed and exposure duration are the two main things. So if you want to make a crisp image in a dynamic scene, you need to either limit the speed of the objects that are moving or the imaging subsystem if it's moving, or also limit your exposure duration. When you do that, when you limit your exposure duration, you're now going to start affecting things like the image brightness, maybe the lighting intensity, perhaps the F number of your lens system, the sensitivity of your pixels, requirements, and things like that. So it gets complex. So when starting with the imaging subsystem, we believe that it's important to focus on sampling and sharpness first because they are high-impact image quality factors. Last thing I want to talk about is evaluation of the system performance once you have your imaging subsystem in place and your algorithm in place. One great way of doing this is with a data set. And it's true that data sets are required for training algorithms, especially machine learning and deep learning. In the traditional computer vision approach, a data set allows you to frequently evaluate performance, and it can give you valuable insights into solutions that are working and not working. And we use a framework. We call it the algorithm development framework, which has 5 sections: imaging subsystem, data set collection, ground truthing, algorithm development, and performance evaluation. And we're using this framework to allow us to collect data, manage data, process data, and to develop and evaluate efficiently. So the imaging subsystem, in this case, is used to collect the data. And ideally, you would have the final form factor of your imaging subsystem in hand before you collect a data set. That's usually not the case. So this framework needs to be flexible enough to allow iteration on the imaging subsystem as well as the ability to collect different sized data sets. The imaging subsystem is placed into a representative environment and attached to a capture tool to collect the data set. Usually in the form of images or videos. And then we have the ground truth or labeling section here. That data set is fed into this section. And in this case, ground truth, we define that as the answer that the algorithm should produce. This usually requires human interpretation to get this in place. For example, in the barcode reader, we had a group of people sit down and identify where in the image the barcode was and what the barcode should be decoded as. And so it's often an expensive step, but what you're doing is creating an asset, a proprietary asset that you can use kind of as a barrier to entry for your competitors. So at this point, you would have a data set with the answer associated with it. You would have that collected in a representative environment with a representative imaging subsystem, and you can go forth with algorithm development. Now this is where you would train your algorithm if you're doing machine learning or deep learning. With traditional computer vision algorithms, we find that a data set with the answer gives us insight into scenarios and problem cases. It also gives us a quick way to do some desktop testing. And once you have that algorithm, then you can do performance evaluation. And we generally call the mechanism this what we say grading tool because we're trying to get a grade on the performance. And all that does is basically take the data set and pass it through the algorithm, and then compare what the algorithm outputs to the answer. And then you can compute a metric, a grade, and then put that into a grade report. And it allows you to track, essentially, how you're doing when you're refining your algorithm. Are you making it worse or better? So this framework is built on a pre-recorded data set, which is great because it allows us to iterate and track improvement. It can accelerate development. But the confidence in our solution is driven by the contents of that data set. So it's really important that the data set be designed appropriately to represent the application space. I don't have time to really go into data set design right now, but we can discuss afterwards if you want to. But it's easy to see here how a data set can be used for performance evaluation. And the power of this framework is it allows for frequent and efficient evaluation, and it provides quick feedback on solutions that work and don't work. So when you use a data set to evaluate your system, in my opinion, it's pretty analogous to like black box testing in the software world. Sometimes, though, you want lower level insights, maybe kind of a unit test. And on the imaging subsystem, one of the things you can do in that case is model your signal path. So these are the components that we highlighted at the beginning around vision-based detection systems. You have your original signal, and then you have all the components that are affecting that signal. And each of those is going to either add noise or be some kind of transfer function on your original signal until you get to your captured signal. What modeling your signal path does is it gives you insights into noise sources and their impact on the image quality. So at Twisthink, we like to say that the first 90%, hitting about the first 90% accuracy is usually pretty simple. It's the last 10% that takes the most time. So when you're working on your last 10%, modeling your signal path can give you the insights you need to find those animals in your signal path that are beating up your signal. So really, modeling your signal path is all about insights. It gives you insights about non-obvious noise sources. It might give you insights into noise sources that need a targeted solution in your algorithm. It might give you insights into noise sources that need further study or experimentation. It might give you insights into noise sources that interact with each other. And you can also use it as a guide for your development by prioritizing low-hanging fruit. So this is a fairly generic signal path that I've created here. You add or remove blocks based on what you would need. In the barcode reader, there might be another block somewhere in there around barcode quality, print quality, or scuffs, things like that. So use modeling to gain insights into noise sources and their effect on image quality. So in conclusion, I've described a couple of reasons why we should start our algorithm development with the imaging subsystem, and I've given you 3 practical techniques that you can take home to be more effective with it. First one is iteration. Use build, measure, learn loops to be focused and intentional on your learnings. Use that iteration to find that right solution that meets your business needs. Sampling and sharpness, they're 2 high-impact image quality factors. Start with these first. Evaluation, use data sets and modeling, and evaluate often. These are my resources. Here are some links to some great articles. Edmund Optics has some great sharpness or MTF types of intros. There's some here about measuring sharpness, and then our website has a link to be able to download this presentation as well as that Excel sheet that we created that can help you accelerate the beginning of your algorithm development. Your imaging subsystem development before your algorithm. So anyway, I thank you guys for taking the time to be here, and I wish you the best as you develop your own detection system going forward. Thank you very much.
Yeah, for questions, please line up at the microphone.
Thank you for the presentations. I think the iteration described the ideal design scenarios. I think this is the best practice, but in reality, sometimes you are short in time.
Yeah.
And you may not have the amount of time you actually desire to iterate as much as you want for the best outcome. So in some of the development process, can you give me some insight out what do you think some of the process can be maybe done parallelly? So for example, like do you think we have to wait, for example, to get the hardware module data before we can actually start the algorithm development, or some of the component might be able to kind of start parallel?
Yeah, I mean, I think the way it usually works out for us is we spend time researching algorithms, and we might use data that's available to us before we collect data from an image, to get some traction on the algorithm first, which can also give some insight into the imaging subsystem, from there on out. Other times, we're trying to use, if we want to do quick data collection, we're trying to use things that are available to us, like a lot of times actually machine vision cameras that have a sensor in it that is representative of what we might be looking at. We can get those quick, right? And you can connect those to your computer with Ethernet or USB to use those. But you're right, they kind of have to, sometimes they have to go in parallel. It's just, if you get too far down in one direction and you have to pull back, that's the inefficiency part that we're trying to avoid, so.
I have a question about your Apple example.
Yes.
If that accuracy detection was neural network implemented, do you actually need to retrain between all of those steps, different datasets?
I didn't retrain.
I know you didn't, but
you could.
Are you should you retrain on a
yes.
blurred data set that also reflects the?
Yep. So I kind of left that out because I was trying to make my point. But yes, if you want your algorithm to be more tolerant to blur, then you need to add blur into your training set, and that will help with those scenarios.
Yeah, I guess the more general question is, how closely does the data set need to match the actual physical implementation of your system, and how much can it be generic?
It really comes down to that trade between algorithm capability and imaging subsystem capability. So if you add more algorithm capability, it can probably deal with more variation on the imaging subsystem side. But if you are trying to create a system that's low cost and low algorithm complexity, then they need to. This is going to be probably trained on what it's going to expect a certain kind of thing out of the imaging subsystem, right? So it comes down to how much capability you want to put into both, I think.
Any more questions? All right, thanks again.
Thank you.